First, I'd like to thank organizers for giving me this opportunity to tell you about recent work on phenomenological description of relaxer ferroelectrics. And this was done in collaboration with Professor Peter Davies at the University of Pennsylvania. Okay, so I'm not going to talk too much about introduction to relaxers, and they have many fascinating interests in physics, but perhaps the two most widely studied and talked about properties of relaxers are sort of their dispersion and diffusivity in the dielectric response. So that's where the name relaxer comes from. It's a relaxed phase transition. You can see that the peak dielectric constant here on the, say, closer to the ferroelectric side is more sharp, and over here on the relaxer side it's a little bit broad, and that's the diffuseness of the dielectric response. Okay, and then there is also the dispersion, which is the dependence of dielectric constant on the frequency. For example, you can see here that as the different frequencies, you have different dielectric constants, and you can measure the dispersion by this delta T dispersion parameter, which is just the difference in the electric constant temperature maximum, let's say at 1 megahertz and 100 hertz. And if you have such a system which is strong relaxer, so it will show a big delta T disp, and if it's a weak relaxer, it's going to have a small one, and as it goes to ferroelectric phase, which is going to 0. Okay, so if you look at the dispersion or relaxation, it's characterized by this Vogel-Fulker expression, where we look at the temperature maximum dielectric constant at a given frequency, and shows this kind of a sort of, not Arrhenius, but Arrhenius-like form, but on the bottom we have T minus T naught as opposed to the usual T. And it's very easy to show that this delta T dispersion that we use over there is basically proportional to the Vogel-Fulker activation energy EAVF. Okay, and for diffusivity, it's been known for about 20 years, following the work of Alexei Bokov, that the dielectric constant follows this quadratic Lorentzian behavior, where how broad your transition is characterized by this parameter delta, and that tells you the width of your Lorentzian. Okay, so these are two parameters that we're going to talk about because they characterize the relaxer behavior. So some time ago, we found that there is an empirical formula that takes the arrangement of BKN arrangement of the lead-based relaxers, and basically the more disorder you have, the more relaxed your system is, and this delta T just parameter squared is just proportional to the sort of average valence variation in a lead-based relaxer. And you can see that it gives pretty nice results over here for a whole bunch of systems. And this way we can sort of predict what is going to be the relaxer nature of our system as a function of BK9 ordering. Okay, so recently Peter Davies synthesized this new material called PBMN-PT, where it's PBMN is lead 1/2, bismuth 1/2 on the A side, and magnesium 1/2, niobium 1/2 on the B side, and solid solution with lead titanate. And he measured the dispersion of this series of materials, going pretty much all the way, the phase diagram, almost up to the pure PBMN end member. And what we found is that whereas the previous sort of champion for lead-based system was delta T disp 37 for PSW, right over here, he can go all the way up to, let's say, 84, which is the limit over here. And if you can extrapolate this to end member, it probably will reach about 90 Kelvin. So this is much stronger relaxer than anything, at least at the lead-based system that we have seen before. And the question is, why, what's going on? And of course, we try to use our old model to see if it fits, and it doesn't fit at all, because the predicted dispersion is 40 Kelvin using the old model, and the experiment, say for PBMN, extrapolated is going to be around 84 or 90. So we're off by a factor of 2 point something. And obviously the empirical model needs a little bit of a fix-up, and it's sort of obvious that it has to do with the presence of bismuth on the A side, but we'd like to be a little bit more specific than that, and that's the first thing we're going to address. So what controls this dispersion in the relaxers? So if we just write down the formula for the relaxation lifetime, which is the same thing as the Vogel-Fulker formula, we have this exponent and the activation, Vogel-Fulker activation energy divided by T minus Tf, and Tf is the freezing temperature. Okay, so we can also write the formula for Arrhenius activation energy, right? Because all these relaxation processes have to follow normal laws of physics and chemistry, and so it has to have some sort of a barrier that the system goes over, and so therefore the lifetime over here can be written in Arrhenius format as exponent of U of t. So this is the temperature-based, temperature-dependent activation energy divided by kT. And now we can take the two exponents and set them equal to each other, right? So here is our U of t divided by kT is equal to U of AL, let's say, KB by T minus TF. and then we can solve for the Arrhenius energy, right? So this is the actual barrier experienced by the system, and it scales as some constant times T divided by T minus Tf, right? So it has this interesting T divided by T minus Tf dependence. Okay, so let's say in classical chemical reaction, you're going to have a fixed barrier. Here the barrier is temperature dependent. So again, very sort of phenomenologically, one quantity that has this kind of a relationship of scaling as T divided by T minus Tf is the polarization fluctuation in the parielectric phase of a ferroelectric material. Right? So P squared divided by Kt is the formula, or is the formula for the dielectric constant, which of course has a Curie-Weiss dependence, and so therefore P squared, this sort of standard deviation or the fluctuation of polarization, has a dependence that's exactly the same as the Arrhenius activation energy for a relaxer. Okay, and so the question is, what exactly is doing this kind of fluctuations? Because we have many different sites in our system in our relaxer, and the question is which ones are responsible. So if you look at, let's say, this is taken from 2009 paper. And if you look at different kind of local environments, so we see that as we cool down from the, let's say, parielectric phase through the Burns temperature into above, let's say, Tf, we see that we have quite a lot of relaxation over here for all kinds of local environments which have niobium and titanium atoms. But we have a magnesium-rich environment which has many, many low-valence cations. You can see that the relaxation lifetimes here basically don't change at all, and the system essentially stays parielectric all the way until Tf and perhaps a little bit beyond that. So it's clear that if there is something that's given these fluctuations, with the transition temperature of Tf, it's not these regions, it's not these kind of sites, it's these sites which are rich in low valence cations, and it must be that these sites are the ones that are responsible for the, or at least partially responsible for the activation energy of this Arrhenius relaxation process in relaxers. Okay, so again, the underbonded oxygen atoms or magnesium-rich environment means weak coupling and fast dynamics. Okay, and so what we do is we propose, again, phenomenologically quite simple idea that since what's important are these polarization fluctuations, and we know that the local polarization of bismuth is much larger than this for lead because bismuth has a bigger off-centering and it carries a bigger Born effective charge. So therefore, it makes sense that the polarization fluctuations for the bismuth-based materials are going to be bigger, and therefore the Vogel-Fulker activation energy or the Arrhenius activation energy is going to be bigger as well. Okay, so this is basically the idea that the U of T, this activation energy of Arrhenius, is going to be proportional to the local polarization squared of the parielectric sites, the sites which are rich in the low valence cations. So for BPMN, we know what those environments are. Roughly, there is some question as to cation ordering, but we can use DFT calculations to figure out what are the polarizations, what are the local polarization of these environments for PBMN, and we can do the same thing for PMN, and then we can get a ratio of these two parameters. Again, the P squared of fast sites for PBMN and one for PMN, it's about 1.5 to 2.7, depending on how you take into account your cation ordering. And then we can use this as a fix-up factor to multiply our predicted delta T disk from the old empirical formula, plug it in using the DFT parameters we obtained for PBMN in various compositions. And here's a comparison. So this is experimental data for PBMN for this delta T dispersion. And now here's the theory with upper and lower bounds because, again, there is some uncertainty as to what is the cation arrangement of this material. And you can see that now the experimental points are no longer a factor of 2 off from theory. They're actually bounded right in the right place. And so therefore this suggests that if you want to understand the dispersion in the relaxer materials, and let's say bismuth including ones, so what we have to do is take into account the variations in the fluctuation polarization of the fast sites. So again, this is a phenomenological description. Why this makes sense sort of energetically is another question, which I don't have a good answer to, but this seems to explain how to relate the structure of and the composition of the material to the dispersion. So okay, this is the dispersion. What about diffuseness? Right, so again, I remind you that you have this quadratic Lorentzian, where the 1 over the epsilon is just T minus Tf squared divided by this 2 delta squared parameter. And what we found in our recent MD work is that when we look at the relaxers, they're characterized by these decoupled and more or less independently fluctuating polar nanodomains. Right? And these nanodomains have fixed size. So for example, between T star and T Burns, we have these dynamic polar nanodomains. I don't want to call them polar nanoregions because it gets me into a lot of trouble maybe, but there are certainly nanodomains. You can see a nanodomain of correlated polarization, but above T star, it changes its position from time to time. So this is, say, simulation time 1, this is simulation time 2, right, a little bit later in the trajectory. And if you go below the T star, then you see that these domains are now quasi-static. They're located more or less in the same time. They do change their shape a little bit, and they certainly change their polarization orientation. But in both cases, they're roughly the same size. So we don't have this kind of explosive growth of polar phase. It's only it grows to a certain size, and or maybe it doesn't even grow. It kind of is frozen, or it appears at a certain size and stays there. And the reason why it's limited to the size is because of, again, these weakly coupled fast dynamic sites, which act as walls, which decouple the polarization in the neighboring cells. Okay, so how do you write what's the simplest way that we can characterize this by Landau theory? We can just take the normal Landau theory of a first-order phase transition ferroelectric. For example, here I took the lead titanate parameters from work of Rossetti in 1997. So we have the second-order term, you have the negative fourth-order term, and the positive sixth-order term. And now, because this is a finite-size object, this nanodomain, and we assume that it's essentially decoupled from its neighbors, so now we multiply this by n, which is the number of the unit cells in the domain. Okay, and then we can calculate the probability, the Boltzmann probability distribution of polarization for each nanodomain, which is given just by exponential of this minus g of p divided by kt. Okay, so what happens if you have a very big size of the nanodomain? Let's say you're very close to the MPB, let's say PMN 30% or something like that. So then you can see that even if you're slightly below the phase transition, say at minus 50 degrees lower than T naught, so we have this fairly deep potential energy surface. Okay, and the system essentially is going to be found all the time right here in the well, in the bottom of the well, with maybe small oscillation in this very harmonic region near the bottom of the well. If you go even 2 Kelvin below the T naught, still the potential energy surface looks fairly steep, less steep than before. And once again, the system is going to be localized in this harmonic region over here. And the same thing will happen when we are, let's say, above TC, or T naught rather, 100 Kelvin above or 50 Kelvin above. And it's only when we're really close, let's say a few Kelvin within the T naught temperature, that we actually, the system is going to sample a broad range of potential energy and have sort of feel the anharmonic effects of this fourth order and sixth order terms. If you go to much smaller size, let's say 16 unit cells, and do exactly the same thing, you can take exactly the same parameters for titanate, so you have something that looks like this, right? And the black curve is once again 50 Kelvin below T naught. The green curve is 100 Kelvin above T naught, and now you can see that the system will explore quite a large range of polarizations, thermal fluctuations, and the potential energy surface will be very anharmonic, not just right next to TC, but quite a bit away from it also. Okay, and so small size basically means they have large polarization of fluctuation of polarization, and our polarization is no longer limited to right around the minimum energy position. Okay, so let's say this is the model. So how can we test it? The first thing we can do, we can look at the evolution of the average local polarization as a function of temperature. So from our MD data, we can calculate the lead displacement, local lead displacement, average local lead displacement as a function of temperature, and that's shown by these black circles over here. And you can see it has this kind of interesting shape that here it perhaps looks like a normal sort of ferroelectric phase transition behavior, and here it looks very different. Actually looks somewhat like a Arrhenius relationship. And when we say set n to 16, and we use the lead titanate parameters and we scale them a bit by multiplying the x and y, so then you can get this red curve, and it fits quite nicely to the black circles. So we see that this is the evolution of our polarization from Landau theory, and it matches, again, the average polarization based on this whole probability distribution, and it matches quite nicely to this black circles, except right here in the parallactic region at T greater than TB. Okay, this is the Burns temperature for these MD simulation data. Okay, and if you see that, if you look, let's say, at very, very large domain size, n is equal to 200, that's the blue curve over here. It looks very much like a normal ferroelectric polarization, nothing special here, and clearly does not match what we see in MD. And same thing if our size is too small, let's say n is equal to 8, that's the green curve. You see that now it's a little bit too broad, and again, doesn't match the profile that we observe in MD. Okay, so by sort of playing around with this fixed size of the nanodomain, we can get the right profile for the MD data, and we can really match the average local polarization that we observe in MD. Okay, so what about the dielectric constant? So dielectric constant is basically the polarization fluctuation divided by KT, or yeah, this is wrong, it should be dielectric constant at 1 over epsilon. So the same thing, we do the same thing. We look at our profiles, we figure out the polarization probability distribution, and we take the second moment, and that gets us the 1 over that gets us the that gets us the dielectric constant. Okay, and then we can plot the 1 over epsilon on the y-axis and temperature on the x-axis. So we see for very large domain size of 1,000, you get this QE-wise dependence, as you should. And right over here, very close to TC, maybe you get some sort of deviation. Okay? If we go to the size of 16, which before we found matches the MD data, so we see there is QE-wise at high temperatures, because at this point, the system does not feel any harmonicity. The potential energy surface is steep enough that you don't feel any harmonicity at all. So it looks like a normal harmonic potential of a normal paraelectric. And therefore, you have QE-wise behavior. At some point, the harmonicity starts to kick in, and now you have deviation of QE-wise, which grows larger and larger and larger, and you have this kind of a parabolic dependence, and I don't show it here, but you can fit it to a parabola, and characterized by the parameter delta in the quadratic Lorentzian expression. Okay, and it's very easy to show that if you change your size, let's say from 16 to 8, you get, say, the green curve, so the Burns temperature now shifts a little bit, and the delta becomes much bigger. And so smaller size means larger delta, and bigger size means smaller delta. And eventually, if you go again to very large size, then delta disappears and becomes 0. And so what we see is that by using this kind of a simple model, we can get the quadratic Lorentzian diffusivity. We can also get this in a very natural fashion, the deviation from QE-wise behavior, just by tuning the size of the nanodomain, and this parameter delta is just proportional to 1 over n. Okay, so can we now relate this dispersion and diffusion? So in principle, both of these are related to the size of nanodomain, because again, bigger nanodomain means smaller fluctuations, smaller nanodomain means bigger fluctuation. That tells you the strength of a relaxer behavior. And so I would expect that these two parameters are related, and in fact they are. So again, delta is plotted on the y-axis, and delta TDS is plotted on the x-axis for a bunch of materials. And you can see that there is a pretty good correlation. Some points are off the line, but it's actually better that way, because otherwise you'd think maybe I faked it or something. But this is real data, and therefore we see once again that the key parameter, I think, in the relaxers is this question of what is the size of nanodomain, which is measured by n, the number of unit cells, and this is something that we can actually sort of figure out based on the number of the weakly coupled fast sites, which is again controlled by this V, the valence fluctuation in the material. Okay, so here are my conclusions. Relaxers are spontaneously nanostructured materials, which are at the same time nanostructured and bulk-like or ordered-like, and both the Vogel-Fulk relationship and the quadratic Lorentzian can be derived from this idea of the small nanodomains which fluctuate more or less independently. And thank you.
Thank you. And yes, please.
So n in this case is just a unit cell. Okay, in this model over here, n16 means 16 unit cells. No, this is a this simulation is 3-dimensional 76 by 76 by 76 unit cells. I'm saying in this model it's just a one-dimensional. It's very simple. It's just one-dimensional sort of electric. In the domain is the the number of unit cells in the domain is n. It's a rough measure because I don't think it's exact mapping. Let's say like n16 that you can count 16 unit cells in here. It's more of a and also this is a I'm taking the tight-knit parameters and applying the PMN, so that's another issue. But this gives a rough scale of what's the size dependence.
Question and short answer, please.
Thank you for the presentation. Do I understand correctly that you use Landau theory that is used typically to normal ferroelectrics?
Yes.
And explain relaxers out of the box?
Yes, it's exactly this, that's exactly the point, that I'm taking normal, very simple Landau theory for one-dimensional ferroelectric, and all I'm doing is just putting in size dependence. And once you put in size dependence, again, the polarization fluctuation distribution looks very different, because it's no longer narrowly sort of focused on the harmonic region.
Thanks.
Thank you again.